Well, hi there. Welcome back to the wild world of volcanoes. This is part four. You should have already seen parts one, two, and three. I'll try to make this part short and sweet. We will summarize the composition and classification of igneous rocks. We can make some general statements. For example, the higher the silica content and the abundance of potassium feldspar, the more felsic the igneous rock will be. Uh, the higher the content of calcium, iron, and magnesium, the more mafic the igneous rock will be. And I should point out to you that the temperature of mafic magma is definitely higher than that of felsic magma. Here you have a neat summary table that describes the composition of igneous rocks. I want you to notice the arrows at the bottom of the diagram. The one on the bottom, the red one, is temperature, and it increases from left to right. The black one above is the content of iron and magnesium. It also increases from left to right. Above that one, you have the blue one, that is potassium and sodium content. It increases from right to left. And above that, you have one in yellowish brown, that is the silica content, and it increases from right to left. Now look at the columns. Uh, the felsic igneous rocks, the classic ones, are granite and rhyolite. Granite being plutonic, rhyolite being volcanic. Uh, what are these composed of? Well, basically, you have potassium feldspar and quartz. Those are your key components of your felsic igneous rocks. Look at the column of mafic igneous rocks. The classic ones are gabbro and basalt. Gabbro being plutonic, basalt being volcanic. The composition of this, you have basically your ferromagnesians like olivine and pyroxene, and on the feldspar side, you have the calcium-rich feldspar, say anorthite. The intermediate igneous rocks, the classic ones are diorite and andesite, andesite being volcanic, diorite being plutonic, and chemically speaking, they fall between the felsic and the mafic. And then you have your ultramafic igneous rocks that are, like I told you earlier, they are more like the composition of the uppermost upper mantle, and the minerals that would predominate here would be your olivines and your pyroxenes. I wanted to show you samples of the ferromagnesians. Remember, we have olivine, we have pyroxene, we have amphibole, and we have the black mica biotite. I did not have a good picture of pyroxene, but let it suffice to say that it looks similar to that of amphibole. So here from left to right, you have a picture of olivine. That's the first ferromagnesian to crystallize in the cooling magma. Next would come the pyroxene, and there's no picture here. Next would come the amphibole, which is the one that you see here in the middle. And then you would have your black mica or your biotite. On the feldspar side, remember that we go from anorthite, which is the first plagioclase feldspar to appear in a cooling magma, all the way through the plagioclase series until you reach the other endpoint, which would be your pure sodium feldspar, which would be albite. And then beyond that, you have your potassium feldspar, your orthoclase or microcline, if you will. The pictures that you see here, the one on the left, is in essence a gabbroic garnet anorthosite. The dark mineral that appears here is anorthite. The picture in the middle shows you a classic example of your white sodium plagioclase feldspar, which is albite. And then the picture on the right shows you an example of orthoclase. In this particular case, it is pink in color, but it could be white or it could be green, etc. This is your potassium feldspar. Your white or your golden mica is muscovite, and you can see pictures of samples of this here. Finally, we get to the point where we have silicon dioxide or SiO2. That is the mineral quartz. And the pictures that you see on the left, you see an example of rose quartz that has been polished. On the right side, the picture on the right, you see samples of both rose quartz and purple quartz, which would be amethyst. And then in the middle, I'm standing in front of a quartz crystal, and look at the size of that crystal. That's what I call a quartz crystal, huh? This diagram is a good summary of the igneous rock classification. On the left side of the diagram, you have granite and rhyolite. Those are your classic felsic igneous rocks. They're in essence dominated by the presence of quartz and potassium feldspar. As you start moving to the right, the feldspar begins to get replaced by your sodium-rich feldspar. So your potassium feldspar is giving way to the sodium feldspar. Now you see the black line. That black line is very critical because to the left of that black line, your quartz content is high. To the right of that black line, the quartz content is going to be low. So when you look at trachyte and syenite, you have rocks that do not contain much quartz anymore, but the feldspar that dominates is the potassium feldspar. By the time you get to andesite and diorite, now you're looking at the classic intermediate igneous rocks. The feldspar that dominates is more of your sodium feldspar and not much quartz. When you get to basalt and gabbro, you're in the classic mafic igneous rocks. The mineralogy is that of olivine and pyroxene, and your calcium-rich feldspar, say anorthite. Now, pumice develops when you have a felsic or maybe an intermediate type lava that is very rich in gas and water. So the rock that develops from that is very light in weight, so light that it actually floats in water. If your magma is mafic in composition, but very rich in gas content, you develop a rock called scoria. Obsidian would be an example of volcanic glass. The lava here cools so quickly that the atoms don't have time to arrange themselves into the neat patterns that you find in a typical solid. So although the rock is solid, the atomic arrangement is more like that of a fluid. That's typical of any glass. So obsidian would be your volcanic glass. Here I want for you to see pictures of three samples. The one on the left is a fine-grained granite. The pinkish looking mineral there is potassium feldspar. The clear mineral is quartz, and the dark mineral would be your amphibole. In the middle, you have volcanic ash from Pompeii. That's the culprit. That's what killed so many people in the city of Pompeii. The picture on the right is your classic volcanic glass, obsidian. Look at the shell-like fracture pattern, or the what we call conchoidal fracture, typical of all glasses. And I think this is a very nice picture that I took of Le Petit Piton. There's actually two pitons, the Gros Piton and Le Petit Piton, that you find in the island of St. Lucia. These are dacite peaks or remnants of a lava dome. You can see those again in St. Lucia in the Eastern Caribbean. So if you get a chance, go there. It's neat, cool place. Well, we have reached the end of part 4. As I promised you, I made these short and sweet. It's the picture on the right, by the way, is that of a portion of the Andes Mountains near the Argentina-Chile border. So see you in part 5.